yesterday we talked about how to graph the sine curve and the cosine curve. I'm going to do just a really quick overview. You all right there, Peyton? No, I missed it. So we took a unit circle, and let's first talk about the sine of theta. In order to create a graph, you need an input and you need an output. I'm sorry, am I interrupting over there? Yeah. So our input were angles, but angles are kind of hard to graph as a distance, so we actually used arc length, which is a radian. So we measured the distance around. So we took that distance and said, oh, it's over here. And then we measured the height, and we created a sine curve. Now that sine curve maxed out at 1, or 100%, and it minimized at -1, or -100%, and it hit every value in between. Okay? This graph has a bunch of what we call critical points, and critical points are actually a calculus idea. A critical point is a maximum, so there's a critical point here, a minimum, which is a critical point there, or what is called an inflection point. I think it's spelled like that. An inflection point is where the graph changes from concave up to concave down, or concave down to concave up. So concave up is a smile, concave down is a frown. And the intersection of those two things is called an inflection point. So there are 3 inflection points shown on this graph. Just so you know, if I had an exponential graph, is that concave up or down? Up. Does it have an inflection point? No, it's always up. If I had an x to the 5th graph, this would be down, that would be up, that would be down, and that would be up. So there are 1, 2, 3 inflection points. Okay, and when you get to calculus, you'll deal more with those. Okay, also, we graphed the sine, but instead of, or the cosine, instead of starting at 1, the cosine starts at, instead of starting at 0, the cosine starts at 1. But the critical points occur at the same place on the x-axis. So there's one at 0, 1, and then at 90 degrees, and 0, and then down here, here, and back up to the beginning. So if I draw that curve, oh, that was pathetic. Do over. Okay. So let's talk about a couple points. What is the significance of those 2 points? Hey, Jackson, you want to come sit up in the front? That's punishment. Sitting by Colette is punishment. For her. Okay, what's the significance of those 2 points? That's when the sine and the cosine are the same, or that's when the wall equals the ground. What is the angle? 45, what's the other angle? Well, it's a 45-degree reference angle in quadrant 3. So down here, it's halfway between 180 and 270, which is 135. How come they don't intersect in quadrant 2? Any idea? Well, in quadrant 2, if I had a 45-degree reference angle, why don't the graphs of the sine and the cosine intersect? Right, the signs are different. So if we were to go halfway between 90 and 180, which would be right here, the wall height and the length of the ground are actually the same lengths, but they're on opposite ends of the axis so they don't intersect. Okay. Are the shapes of the sine and the cosine graphs the same? How do we know that they're the same shape? We built them yesterday. That might help. We use the same spaghettis, right? You can use the exact same spaghettis for the cosine curve as you can with the sine curve. What's the difference? Sine starts at 0, cosine starts at 1. So how do the two graphs compare? So I'm going to slide which one? Okay, slide. So let's slide the cosine. Which way do I need to slide the cosine? If I slide the cosine to the right, how far? Okay, let's slide it the shorter way, which is to the right. How far to the right do I need to slide it? Not half of. So 90 degrees or half of pi. So if I were to take the cosine graph and slide it 90 degrees, and if I were a good drawer, they would be the same. So what you're telling me is that the sine of theta is equal to the cosine of theta minus 90. Because a horizontal shift is always opposite in the world of translation. Right? If you had x minus 2 squared, that's to the right 2. Anyway, we'll get to that later. So theta minus 90. Well, we already knew that was true, right? We know that sine and cosine are complements. So if you do 90 minus theta, if you do sine of theta, then the cosine is 90 minus theta. Now, that ends up being negative. There's more at work than you realize. But all you have to do is shift the cosine and it equals a sine graph. Or you could shift the sine graph and equal the cosine graph. Either way. All right. So, if I have y equals the sine of theta, this is an angle. What does the sine mean again? Well, opposite over hypotenuse, but when the lateral is length 1, sine is, it's simply the wall. And we represented the wall by breaking spaghetti pieces. So I should be able to transform the sine graph with my knowledge of angles and spaghetti pieces. For instance, if I had y equals 1/2 the sine of theta, what do I need to do? Cut what in half? Well, the graph has two directions, right? It has angles going left and right, and it has spaghetti going up and down. So what am I going to cut in half? Well, this says half of the spaghetti pieces, the wall lengths. So if I were to graph the regular sine, and I put my critical values, I don't care if you write them there, and then it goes from 1 to -1, what is 1/2 sine of theta going to look like? It's going to be half as tall, because we're cutting all of the spaghetti pieces in half. What about y equals 2 cosine of theta? So the normal cosine, and this is how I like to do it. So here are my critical points. Right. So 2 cosine of theta is going to be twice as tall and twice as short, as low. Okay, that's pretty easy. What about sine of theta minus 2? And if those are in parentheses, then it means they're together. But if they're not in parentheses, then they're separate. So sine of theta minus 2, what would that mean? you're going to take your normal spaghettis and you're going to drop them 2 units. So if that's my regular sine, this point is going to come down to here. Oops. And my center line is going to be at -2. And my minimum is going to be at -3. And then just draw the sine curve. Does that make sense? So a number in front changes the height. A number behind just changes how high or low the center line is. So if I had something like 3 cosine of theta minus 2, what's that going to look like? 3 times taller, and the center line is down 2. So if I draw my graph, 1, 2, here's the center. Where does the cosine start? At 1, unless it's 3 cosine, then it starts at 3, but if my center line is 2, it's going to start at 1. So there's my center, 1, 2, 3. 1, 2, 3. And then that's my cosine curve. Does that make sense? Okay, I want you to graph these by hand, and then you can check them in your calculators. But it's good to know how this transformation works. Okay, so pull out your calculators. And type in the sine of x. You'll notice that the x button actually says x, t, theta, and n. So anytime you're graphing a function, no matter what the input variable is, whether it's an x, a theta, a time, or a natural number, you always just use x. So graph the sine of x and push graph. I see 2 little marks on mine. Okay, or you might have had a sine curve, but it's kind of hard to see because it's small. Why does mine not show up? I'm in degrees. What is the period of sine in degrees? No, the range is from -1 to 1, but what's the domain? Well, it takes a full revolution is from 0 to 360. So it takes 360 degrees for a sine curve to go through a full cycle. So I could change my window, or if you push zoom, number 7 says Z trig, and it will match the window to include from -360 out to 360. Zoom trig, zoom number 7. There might be one on my desk. Yeah, it looks like there's one. Dead as in no batteries, or dead as in dead? Oh, that's right. Yours is fancy. Okay, so what if I switch to radians? So I'm going to push mode, and I'm going to go down to radian and hit enter. And then I'm going to regraph it. Well, now I'm showing 360 radians, which there are only 6.28 radians in a circle. But if I push zoom trig again, so no matter whether you're in degrees or radians, if you graph a trig function and push zoom trig, the picture is going to look exactly the same. The window is different. Zoom trig will take it from -2 pi to 2 pi if you're in radians, or from -360 to 360 if you're in degrees. Okay? So graph these by hand, and then follow up by graphing them on your calculator, making sure you're in the right place. Okay? But that's for homework, so we're going to move on. Here's something that I want you to watch, but you don't need to duplicate that. So we did vertical transformation, and we did, well, we did vertical, whether it was amplitude, how high it is, or just shifting it up and down. What if we mess with the x-axis? So y equals the sine of 2 theta. What would that look like? Twice as wide? Well, let's think about it. Let's graph the sine of theta. So I take my unit circle. As I travel around the unit circle, I create lots of wall heights. And I transfer those wall heights over here. So my input for one cycle is every angle from 0 to 360. That's my theta value. What happens if I plug in 1 and we graph 2, and I plug in 2 and we graph 4, and I plug in 3 and we graph 6, and I do that all the way up to 360? So I will input from 0 to 360, but I'm going to graph from 0 to 720. So if my input is from 0 to 360, what is my output going to look like? It's going to be twice as narrow. It's going to have the same height, but it would look like that. Because I put in a range of 360 degrees, but I doubled that, so my output was actually 720 degrees. So what that does is it smashes 720 degrees down to 360, so we have a double cycle. So when you multiply an angle, if you multiply theta by a number, you actually shrink the period. We cut the period in half. What if I did the cosine of theta over 4? What would that look like? So the normal cosine looks like that. From 0 to 360, how much of the unit circle am I going to get through? A fourth of it. And then another fourth, and then another fourth, and this is going to have a period 4 times longer than the original. Okay? What about y equals the sine of theta plus 45? What would that mean? So here's my unit circle. My normal sine curve is going to look like this. And that's because I started at 0 degrees. But in the amended function, if I start at 0, I'm actually going to start at 45 degrees. So if my first point is right here, then if I take this graph, there's the 45-degree mark. Which way do I have to slide the curve in order to bring that 45-degree mark over to 0? To the left. So if I add 45 to the angle, so if I start 45 degrees after where I'm supposed to, I need to shift my graph to the left. And notice this number on the inside is working opposite what you would think. Right, good question. So if I had the cosine of theta, that's the sine of what? Theta plus 90. If I add 90 to the sine, then I push it 90 degrees to the left, which would line up with cosine. Right. And so if I started my sine here at 90 degrees, that's the same as starting my cosine here at 0. See how those all match up? Which is, we already knew because we knew that sine and cosine were complements, right? The sine of A equals the cosine of B. The sine of theta equals the sine of 90 minus theta. which is essentially the same thing that's going on there. Okay, so let's graph the tangent. The tangent is a little bit strange. The tangent does not care what the length of the ladder is. In fact, you can't graph tangent in terms of spaghettis, because tangent is the same as sine over cosine. Well, the sine is just the wall spaghettis, and the cosine is just the ground spaghettis, and the spaghettis cancel. So in order to graph the tangent in spaghettis, you need to find the percentages and then multiply them by the length of your spaghetti, which is a mess. So we're not going to do it that way. We're just going to graph them in percentages. So you have a list of percentages here. Tangent of 0. Well, I'm going to type in the tangent of 0, and I get 0. That was nice. Tangent of 15. Doesn't make any sense. Shouldn't tangent be positive in quadrant 1? Because the sine is positive and the cosine is positive? I'm still in radians. So you need to make sure you know what mode you're in, because if you're in the wrong mode, you're only going to get the right answer at 0. There will be no other answers that are the same. So push mode, I'm going to go back to degrees. And then you don't need to re-enter the information. You can just push enter. 0.26. And for what we're doing today, 0.2 is enough. What does 0.2 mean? 20% of what? The wall is 20% or 20 whatever percent as long as the ladder. As theta gets bigger and the wall gets longer and the ground gets shorter, this number should go up. So tangent of 30 is 0.5. What happens at 90 degrees? It freaks out because the ground has no length, so the answer is infinity, or actually something else. You'll see that. So go through, fill out all of these values. If you get done, then I want you to graph the values on the next page. So you have a graph, you have your degree measures, and you have your percentages. So the first point goes at 0, 0, and then 15.2, and then 30.5, and then 45, 1, and so on. Now these are obviously going to go off the page. If it goes off the page, just ignore it. So go through and calculate all of those tangents, and I'll pause the video. So take the numbers on this page, go to the next page, and I'll leave this up here so you can just look at this and graph. And graph all of those points. Now obviously, when you get to the tangent of 84, it's off the page. And it's off the page until you get back to the tangent of 105. So just graph the points that fit on the page. Don't connect the dots yet. We'll talk about them. 0.2 is a fifth of 1. Couple things. Looking at this, what do you notice as we get closer and closer to 90 degrees? The percentage gets larger and larger and larger. So if I approach 90 degrees from below, so if I start at 0 and I approach 90 degrees, I approach infinity. But what if I start from above? I approach negative infinity. And you can see that on the unit circle. In quadrant 1, if I travel in this direction, the wall is getting higher and the ground is getting shorter, so I'm approaching infinity. But if I look in quadrant 2, and I approach from this direction, the ground is negative and the wall is positive. And as the wall gets larger, as I get closer to 90, the ground gets shorter. So this is 1 over negative 0. So it actually approaches negative infinity. So not only is the tangent of 90 not a real number, it's two different numbers if you approach from different directions. So tangent of 90 is simultaneously infinity and negative infinity. It just depends on which direction you're coming from. Okay? So if you draw a graph, 90 is going to be a problem. And if you miss the graph like I just did, you can always just slide it over. And then 270 is also going to be a problem. And your graph is going to look something like this. And then it's going to start down here at negative infinity, intersect at 180, and then go up. Are we going to reach those vertical lines? No. If you have a graph, a line that a graph approaches but never reaches, that line is called an asymptote. So the first question underneath the graph says, what is an asymptote? It's a line that a graph approaches but never reaches. A line that a graph approaches but never reaches. Peyton, you graphed yours upside down. Well, the first half's okay, but these numbers are supposed to be negative. You hate your wife? Oh, your life. Okay, so why does that happen? Why does the graph not exist at 90 or 270? Why is it infinity? There's no ground. So at 90 degrees and at 270 degrees, the ground equals 0. So the ratio of the wall and ground is an infinite percent or a negative infinite percent. Yes. Because at 90 and at 270, the ground is 0. When the ground is 0, the wall is infinitely longer than the ground, or negative infinitely longer. All right, pull out your calculators. Let's graph the tangent of x and see what it looks like on our calculators. So tangent of x, graph. I'm already in zoom trig mode, and yet it still didn't work. Why doesn't it work? My zoom trig was set for degrees, and then I transferred my calculator into radians, so yours might have worked. But if you have a trig graph that doesn't work, just do zoom trig and it will convert it for you. Tangent of x. Now, some of you might not like how slow your calculator graphs, and if you're doing most graphs, you can turn up, it says turn up the resolution, which is not really the right way to put it. Zoom trig. Okay, so if you go into Window, down here at XRes, you can change the resolution, how fast you want it to graph. But if you speed up the graph, like level 4, then it won't be as clean, and sometimes the asymptotes show up. Well, you can go as high as level 8, but watch what happens if you graph it 8 times faster. It'll be really quick. So if you're doing a parabola, it's not going to make that much of a difference. But if you do any trig function, or if you do any really complicated function, the more you speed up the resolution, the worse that it looks. What does 2 look like? Let's check. So if you want to speed up your calculator, you can, but every time you speed it up, you lose the smoothness of the graph. I don't think you can go below 1. I don't think it'll let you do a decimal. Let's see. Yeah, it won't let you. So if you do 0.5 and you push up, it gives you an error. So the lowest you can go is 1. And I think 8 is the high. What's that? Exactly. Well done. Well done, Connor. Okay. So look down here. Where are the asymptotes of tangent? Yep. No, it's not 180. 90. So the first asymptote is 90 degrees. Where are all of the others in reference to 90 degrees? How much more? 180 degrees more or less. So I can say all of the asymptotes are represented by 90 plus 180 times n, as long as n is, well, it could be 0, could be 1, could be -1, as long as n is an element of the integer set. Because negative n's would put me on the left side of the y-axis, and positive n's would put me on the left side, on the right side. So we can draw those asymptotes here. Every 180 degrees, there's an asymptote. And then the tangent just repeats over and over. Yeah, starting at 90 every 180 degrees. So what is the period of tangent? 180 degrees. It takes 180 degrees to do a full cycle of tangent. But wait a minute. Yes. How come sine and cosine had a 360 degree? And tangent only has a 180 degree period. Okay, I'll agree with that. How come the top half of the graph of tangent is exactly the same as the bottom half of the graph of tangent? Why is that the case? Okay, so you're saying the wall starts at 0, maxes out, and minimizes. But over here, it starts negative. So shouldn't half of it be positive and half of it be negative? Do you remember all students take calculus, or all suckers take calculus? I never taught you that. This tells you which one is positive in each quadrant. So they're all positive, sine is positive, tangent is positive, and cosine is positive. So tangent is sine over cosine, y over x. So this is plus plus, minus plus, minus minus, and plus minus. Well, you do this a lot in calculus. Yeah, trig is a huge portion of calculus. I mean, like half of it is trig. So if you notice, all of the angles are the same, all of the wall and ground lengths are the same in quadrants 1, 2, 3, and 4. The only thing that changes are the positives and negatives. So tangent is positive here and negative there. The values are the same. They're just on opposite ends of the x-axis. And then positive here and negative there. So the top half is exactly the same as the bottom half. So tangent has half the period of sine and cosine. Okay, you need to finish that worksheet for your homework tonight. Have fun. Sure.